So we have our standard legal disclaimer. This is not a product, blah, blah, blah. My name's David Chase. I work for Oracle Labs in the Programming Languages Research Group in Burlington, Massachusetts. This talk is about how we implemented dynamic overloaded dispatch and generic type inference in Fortress. I'm presenting this. This was very much a team effort, and most of the people who worked on it are listed there. So the first thing to know is Fortress was a long-running project. It was started under a DARPA grant to improve the productivity of high-performance computing. Our slogan was, "Run your whiteboard in parallel," and had a bunch of difficult features: space-sensitive mathematical syntax, work stealing, load balancing, transactions, not just transactions, but nested transactions containing parallelism in the presence of all this load balancing fun. Has generic functions, generic methods, traits, and objects. And this talk is about just one of these features, which is the multi-arg dispatch of overloaded functions, where the overloaded functions themselves can contain generic functions that need to be inferred and instantiated. And it's important to understand this language has a type system. It is statically checked. There will be no runtime type errors, but it's very much dynamically inferred, and you could almost think of it as dynamically typed. First thing to note, simplest example of Fortress dispatch. You're a novice Java programmer, you go to write your class foo, has an equals method, and you try the first one. It's commented Fortress dispatch. It's just, well, I handle the foo case, and I still have to handle the object case, and objects aren't foos. Great, I'll return false. And of course, this doesn't work in Java. And experienced Java programmers know that they have to write the object equals, which then says, am I really a foo? Oh, I am. Go there. When we're done, this is exactly the code that you would get for this simple dispatch case generated automatically. But we want to do a little more than the simple case. So you could imagine you had a numeric hierarchy, and up at the top you have rings of things. And if you have two things, you can add them and multiply them. And if you have a matrix of things that are in a ring and another matrix of things that are in the same ring, you can multiply those matrices. And so you certainly write the general case, and now you're done. But it turns out there's a lot of special matrices, and there's diagonal matrices, and there's special representations of matrices and distributed matrices. And you want to write a different overload for all of these different kinds of matrices. And you don't want, it might not be statically evident which one you're calling. You just want the right thing to happen. And you might think of a new matrix late in the game that you want to add. And so here, not only do you choose, say, the right function, whether it's diagonal or not, but you would also burn in the right type once you dispatch to it, whether your T is an integer or a complex or a real. You would really like that generic thing to be instantiated and templated out, and the calls made much less general and more specific. We have here sort of a special case. You can extend matrix of bools and multiply by them. They map pretty naturally to multiplicative integer and 0 for whatever ring you're talking about. Before I can go too far, I need to talk about the Fortress type system quickly. There's a type called any that's at the root. Below that, it's divided into 3 parts. We have tuples of things. Tuples are covariant. We have arrows of things. They are invariant, arrow covariant. But what we're mostly interested in here is the object hierarchy rooted at object. Here I can even point to it. And within the object hierarchy, there are traits, which can be generic, and objects, which can be generic. Traits are like interfaces with default methods. And objects are like final classes. Traits can be invariant or covariant in their various methods. Fortress has a special thing that we call selfless traits, described on the next slide. At runtime, you will also see union types and intersection types produced by type inference. And Fortress also has a way of declaring that two types can never be in the same place. You cannot extend dessert topping, and floor wax simultaneously. The selfless generic types we use to deal with binary operators and algebras. They're called selfless because when you instantiate one of these things, you extend it and you instantiate it at the same time. And the selfless type, the selfless generic, doesn't really have its own self. It has to get it from the type that instantiates it. But what you then get is that T is T, self is T, and these things all match. This is just a simple trait for comparable. If you extend comparable with your favorite type and provide a less than, we'll default all the others in there and you're good to go. You might want to override them to be more efficient, but you don't have to. This is my example overloaded function. We'll return to this later with a worked example. And the idea here is you have the comparable type, comparable of T, and it excludes list of T. They're both objects, they're both traits. And in addition, we have integers, which extend comparable of integer, so they are themselves comparable, and string, which extends comparable of string. So they are similarly comparable with themselves, but not with integers. And then we have an overloaded function compare, an operator really. And I've sorted these, as you see at the bottom of the slide, into most to least specific order. So we have the boring leaf types at the bottom, string and integer and integer. Both of these overloadings are provided because you want them to go fast. Then we have the general one in the third position. So for any pair of comparable things, you can compare them. The fourth one, lists are not comparable, and in fact, because of the way this is declared, they can never be comparable. But if you had a list of comparable things, you could do lexicographic order with another list of the same or comparable things, and you could compare them. So you want to add this overload. And then finally, just because you like getting exceptions, you can compare a pair of objects. And so this is overloaded. It has generic entry points, and the generics have got type parameters yet to be bound. And how do we implement this? So we sort this into a most to least specific order, and in Fortress we use types, but it doesn't have to be types, it just has to be in order. You could start with a partial order and topologically sort it. Once you have that order, you just sequentially test applicability from pretty much best to worst, and the first one that hits is the winner. Now I'm presenting it like this because this was really quite hard to get right, and so this is more to convince you that it is made of simple steps that could be optimized, and we did it right. Optimizations would be that much harder to explain. So we had the step, test applicability. How hard could that be? So what do you have at runtime? You have a bundle of arguments, and they have nice types. No variables in these, ground types, fully instantiated. And on the other hand, you have a signature for the entry point, and it might have type variables in it. So you need to pattern match these two, and if the patterns can match, then it can apply. Pattern matching is easy if the signature has no variables. That's just a bunch of instance of checks. Nice, simple, fast, what we know from Java. But that's easy. We're worried about the more annoying case. So instead, you're pattern matching, and along the way you encounter type variables, and where they match up, you accumulate constraints on the parameterized type occurrences in the entry point signature. You'll have upper bounds and lower bounds based on the variance. After you pattern match and collect constraints, there will be interrelationships between the constraints from the function's generic signature. You propagate these constraints across and close in the lower and upper bounds. And if the answer is a bunch of non-empty sets, you win, and you can go to that function. So, we're all done now, right? Except in general, this is not well defined, and in general, this is not very efficient. And, I don't even know for sure if it terminates. So what did we do? We had to make a bunch of restrictions in our type system, and some of these you say, oh, very, very reasonable, but we really had to do all of them, and you will see them popping up again when we work the example and go through sort of how we do this. From a given type, your path through supertypes to any, all those paths have to be finite. No infinite chains. For now, we only let unions and intersections appear because of type inference and not because the programmer declared them. This makes them a little bit less pathological. We don't want them to, I see you making a face. We don't want them to appear in signatures where you have a union of something with a type variable. That makes the pattern matching harder. And you can imagine appropriate special cases where you would allow them, but we have to actually define them. For each generic supertype, so foo of t is a generic supertype, or bar of t is another separate generic supertype, there must be a minimum instantiation and it must be declared. This means, for instance, that you could not extend foo of string and foo of integer without extending something else that was both a foo, that was both a string and an integer, and you had to declare that you extended it. So this has to happen. The selfless traits are a little weird. They have to be singly inherited. So for any given selfless trait, say ring or field or comparable, if you look at all of its instances, they form a forest, not a DAG. We impose restrictions on function type constraints. They have to be sort of ordered, and so you can accomplish this by saying that they're scoped, and you cannot use them before they are declared going from left to right in the parameter list. And there's a particular form of the constraints, so the newly declared parameter can only extend some type expression of already declared parameters. Again, there's a special exception for self-types. They can extend themselves. Big restriction, no contravariance, period. Just couldn't get around it. But we did find a workaround for what we consider the useful cases of contravariance, and that made us very happy. So if we have these restrictions, what do we do? By the way, you don't necessarily need to understand this. This is intended to sort of illustrate the strategy. We will work an example later. So we have a match procedure, and we're going to partially evaluate it, and that's the compilation strategy. And all of the green stuff is where we expect to find constants. Match takes G, which is a ground type, that is the incoming parameters types, the incoming argument types, excuse me. V, which is a variance, 0 for invariant, 1 for covariant, and the last parameter is S, which is a type. It's the signature type, and it may contain type parameters. And over here on the left, we have the simple cases where we have ground type versus ground type versus a bare parameter. Arrows and tuples we take care of, could be a union. Intersection types are in the backup slides if anyone really wants to see them, but it wouldn't fit. And then we have this last section here, which is on the next slide also. So here you have something more complex than a bare type. You have a generic type in your signature, and the generic type contains type variables. And the ground type is not a union or an intersection, blah, blah, blah. So what do? We lean on this restriction for the minimum ancestor and say, well, the signature type has a stem of T. I want to know if the ground type has a stem of T. And I want to know the minimum instantiation of that thing, if there is one. If there is one, then based on the variance, and the variance is known because it's in the signature, so this can all be burned into the compiled code, recursively test all the parameters and see if they satisfy the constraints. And if so, you win. So this is pattern matching, and along the way we collected constraints. The second part here is constraint propagation, and again we partially evaluate this chunk of code. Again, the green stuff is compile time constants. Here we rely on the scoped property of type parameters. So we would go from right to left. The rightmost parameter, nothing can depend upon it. It depends upon everything else. The form of the constraints forces it to be below other stuff. Nothing is forced to be below it. So starting from that end, you infer things as low as you possibly can in the type lattice. Low is good, low is specific. Low means that you will get the most specialized code out of the overloading and the best specialization for your generic when you instantiate it. And low also gives you the greatest freedom to instantiate the remaining parameters so that you can actually succeed in the dispatch. So you go from right to left. Your first step is you get the least single upper bound of all the lower bounds. For Fortress, this is the true lattice join. This is where union types can come in. Java might use the lowest common class. You could imagine simply looking up in the type hierarchy and finding the lowest common class, whatever it is. It might be an interface, excuse me, class or interface. Might be an interface, not a class. Doesn't matter, it just has, this is parameterized by your language, really. You have to get the single one that fits your type semantics. Your next step is you iterate over the selfless type constraints, these binary operator things, and you need to find a simultaneous solution to all of them. It's statically evident how many of these there are. A 0 is common, 0 is easy, 1 is trivial and not an iteration. Beyond that, you have to iterate. Based on that, you boost the estimate, your candidate, upwards. Now that you have a candidate, you push that back into all of its occurrences in the other type parameters, which will move their type bounds, their lower bounds upwards, typically. And you do that by recursive calls to match in the same way, passing a ground type, covariance, and against the upper bounds expressions that occurred, which look like signatures. Finally, you iterate over all of the upper bounds in the set for the parameter. And this can also be statically evident if there are none. So this can also be omitted. And provided that the lower bound is below all the upper bounds, you win, and the lower bound is your choice for that type parameter. Repeat till you get to the beginning of the parameter list. So in practice, this is the worked example for the comparison function. And supposing we had that overloaded function, and supposing we passed it a pair of lists, one cat dog and the other bat rat, so a pair of lists of strings. The first one fails. The code that's compiled for the first clause, the signature, has no variables in it, so it's just a subtype test. Is the tuple coming in a subtype of this constant tuple? It is not. Same for the second one. Is the tuple coming in a subtype of tuple of integer integer? It's not. The third one is a more complex compilation of the match procedure. Here you have type variables. Here you need to say the tuple coming in, is it a tuple? It is a tuple. You know, it could have been a single, and it could have been a 2 or a 3 or a 4. It has to have 2 elements. Let's call them G1 and G2. We expand recursive calls to handle a different case of a generic in T, now that we've dispatched the outer tuple. And it's not the easy cases, it's not a union, so then we find out, is it a comparable of something? It's a list of something, it's not a comparable. Dispatch to this arm fails, so we don't go here. The third example is like the first example, except that it wins because it's a string, and you know, this is the case that matches, and the two T's are comparables within a list. And it all works, and the lower and upper bound sets all get set to string. Below we have the partially evaluated constraint propagation. The least single upper bound of a singleton's easy, it's string. The constraint check is easy, it preserves it, it's string. There are no ordinary constraints, selfish constraints. Then we do the upper bound check, string works, everything is good. If we'd called it instead with a different pair of parameters, one cat dog, the list of 2 strings, and the other 3, 4, the list of 2 integers, it proceeds much the same, except you gather different lower and upper bound sets because they're string and integer, and you get to the constraint propagation. The single upper bound in Fortress is a union type, string union integer. You hit the constraint check for the selfless types, and it fails because it's not comparable. So that also works. It excludes the one that you want it to. I don't know how I'm doing for time because I started. Okay. So we did have some runtime type operations that I just called as if they were primitives, and they're not in the JVM. So I'm doing A, is A a subtype of B? If A and B are generic, what then? I'm doing joins or these upper bound operations. That's not provided by the JVM, and it's sure not for the generics. And then we have our own special little operation. Does it have this stem, and if so, what's your minimum type parameters? Where do we get these? And can this be done cheaply? And what we have is I have a candidate data structure here just to convince you that I'm not blowing smoke. If you can define the longest erased path to any, now we're relying on no finite paths. Or it's a recursive definition, pretty simple. Just any is 0, object is 1, and for a trait you take 1 plus the max of the longest path of all of its supertypes, and it's a syntactic definition straight from declarations, ignoring type parameters, easy, not hard. Once you have this, you can then come up with a data structure. You would associate this with each type, we'll call it supers of T, and it's an array, and it's indexed by longest path, and each array element is a map where the domain of the map is types or generic stems, and the range is the minimum instantiation. And the subtype test, first you check the longest path links to be sure it makes sense to index the array, look for the member, and if you expect it to have type parameters, you look them up and you get them, and then you potentially have to recursively do the test for the type parameters individually based on the variance. And a lot of this can be done statically if you are doing this against a constant type. So not hard. This is a JVM talk, and what we're doing is, we're trying to embed some stuff in the JVM that it really was not designed to do. We're embedding our own type system, and we're embedding our own dispatch. And our implementation makes a lot of use of applicative caches. And by this, you have like an applicative balanced tree, and you don't lock for the read, you declare the root to be volatile, and you do an update with a speculative insertion and a cas. And if that works, you're great. And what you want is the common case is reading, and you want that to go fast. But in the end, you've still got this volatile thing, and that's going to inhibit your JIT from doing some optimizations that you'd like. A variant on this, some of our type data structures are lazily initialized. And again, lazily means that they might not get initialized until later in a concurrent context. So we have to worry there. And again, we're using volatile. It's a write once data structure. And again, it can inhibit optimization later on. Method handles and invoke dynamic might help us with these things. I could build an applicative cache by building an executable lookup table, and maybe that's the right thing. I don't know enough about that yet. Our types are not Java types, and type unions and intersections and tuples and arrows have vast numbers of supertypes, and we cannot pre-declare them. And so we're outside of the JVM there. And similarly, our type constants might not look like constants to the JIT optimizer, to whatever optimizer is in there. And so our instance of test will not then make the following check cast go smoothly. We would like that, but we don't have it yet.
David,
yes?
when you say vast numbers of supertypes, are you talking about supertypes beyond those counted by the distance to any metric?
Well, if you take a 5-tuple of string, that's got 32 supertypes of the various combinations of string and object.
So it has a statically computable distance, but impractical to compute set of supertypes.
Very wide. One thing that is clear is that some of the optimization opportunities appear only after we've done the generic instantiation, because often when you instantiate with a very specific type, you'll then discover that all sorts of overloaded invocations within the stamped out function that you just expanded are not so overloaded anymore. And you can erase all sorts of arms there. And in fact, it might be a candidate for inlining, and you really want to do a lot of stuff. And part of the problem here is that from our point of view, we have to optimize some, and then we have to hope that behind the scenes, someone else will optimize some. And we're handling it right now with the class loader from Heck. but so, based on those issues, we might propose some changes. And write-once variables would be cool. We had once upon a time talked about how wonderful it would be to have some lighter weight volatile for these kind of applicative things, but I'm very, yes?
Why do you need a volatile right to update your cache? You don't care if it's
I work, so it's very interesting. I saw a talk where they talked about many people understanding the Java memory model. I work with someone who says there's a half dozen people who are said to understand the Java memory model. One of them is supposed to be me, not me, Victor, and that scares me. And so I do this exactly by the book. If you can't point me to a semantics document that says it's okay, I won't do it. And no one, I talked to the experts. They said, do that. So I do. But I really don't want to mess with the Java memory model. One thing that would be really cool would be if we could declare some methods idempotent. This is very tame, boring optimizer technology. And you could even just wrap your volatile accesses inside something that was idempotent, and that would get me what I wanted, which would be kind of cool. The optimizer would see the idempotent method and comment them up when it could, and when it couldn't, it would say, look, a volatile access, and it would do it right. I'd like that. We think interface injection would solve some of our multiplicity of types or supertypes problem, because even though there's a bazillion of them, we don't really query all bazillion. We'd make a small number of queries, and if we could just register the common case and have that go through a fast path, we think that would be nice. We think unerased generics are really cool, but we're a little reluctant to say, yeah, you should do them, because we ended up with a very specific set of restrictions, and I'm sure we would get into arguments with people about whether or not our restrictions are the right restrictions, and then we might lose, and that would be sad.